Hi. So in this lecture, we will learn about second order linear differential equations, ordinary differential equations. You all already know by now what an ODE is, ordinary differential equation. It's an equation with only one independent variable. Now there are a bunch of other terms here. One is order, the other is a linear. So here's an example of a second order linear ordinary differential equation. So the order here refers to the maximum differentiation that has happened, because we take x as a function of t, or time in this case. If it's differentiated twice, which is the maximum number of times it's been differentiated, so it becomes a second order linear differential equation. Why is it linear? Is because, these terms, these functions here, x is a function of time, d2x dt2, dx dt and x, they're all set up in a linear fashion with constant coefficients 1, b and c. Okay, so that's why that's a linear combination of three variables here. Okay, one is the second order term, the first order term, then the zeroth order term. Zeroth order because it has not been differentiated at all, so that's a zeroth differentiation term. And you can have some function of time, ft, on the right hand side, which is normally called the input or an external force, depending on what the situation is. So that's an example, but we have drawn here a diagram, a physical example. We can't really study linear, differential equations without referring to, examples from physics, because that's where they come from. So here's a very simple example. It's a model, and it's just one of the models. There can be many other models, which all give rise to this kind of a differential equation. So let's study one of them. So suppose you have a body which is, think of it as a point particle, which is suspended from the ceiling by a spring. It has its own force downwards, where the mass and the acceleration, the product of them, is pointing downwards. There's the spring constant K, which gives the stiffness of the spring and how strong the spring is. That is opposing the motion, in the sense that if the body is moving downwards, then Kx, which is the spring constant times how much it has been displaced, that is pulling it upwards. And you have another resistance term here, where if the body is oscillating, it will be experiencing some kind of an air resistance or friction through the air, and that depends actually on velocity, on how fast the body is oscillating. So if you're moving, if you're running, you will feel the air against you, very hard. And if you're walking, you won't feel it that hard. So, the air resistance or the friction is more if your velocity is more. So it really is proportional to your velocity. So this particle will have an air resistance proportional to its velocity. But of course, the proportional constant, we're calling it eta, which is the air resistance constant or the frictional constant, which is opposing the motion. If the body is moving downwards, the opposition by way of the friction is in the opposite direction. Right. So that's what the system is. Now you could also have some kind of an external force. This is the system by its own. It will move on its own, it'll do some kind of an oscillation, it'll come to a standstill because there is an opposition to the movement. So it'll behave in its own way. But you could, in principle, have some kind of an external influence on it. By influence, I mean a force. So you could be, for example, poking this body with your finger from time to time. You could have a string attached to it, and something could be pulling that, or whatever it is. There could be an external force, and it's not important which side or which direction the force is pointing, but let's just say the force, which it depends on time. Okay, I'd say for this example, the force is pointing downwards. It could be pointing upwards, and you will have the minus ft. Now, that's the free body diagram. If I have to translate that into an equation, you would have, by Newton's laws, the mass into acceleration would be equal to, well, whatever this force is, okay, minus, because these are also forces but in the opposite direction, you will have the force from the spring and you will have the force from the velocity, which is the frictional force. Okay, that's the equation from this free body diagram. And if you sort of rearrange this a little bit, if you divide by m, we take m to be non-zero because m is the mass. It has some legit mass. So if I divide by m and you rearrange this a little bit, what you get is x double prime. You bring this to the left and you divide by m, so you have a plus eta by m x prime, and then you bring this to the left, you have k by m x, and then then this you keep on the right, ft, and you divide this by m. Okay, this is in the same form. Okay, it's just that eta by m is now written as b, k by m is written as c, and this capital F of t by m is written as small f of t. Okay, so really this is the model which gives rise to equations of this kind. There are, as I said, various other models. You could have a pendulum, you could have a machine that is heating up, all sorts of such models or examples which give rise to the same form of equation. Now, if you don't have this external force, then this right-hand side will be zero. Okay, then it would be a system on its own without any external influence. And that would be called a homogeneous or a null differential equation. Okay, so if ft is zero, the right-hand side is zero, in that case, this would be called a homogeneous, second order ordinary differential equation. Okay, right. So the question, of course, is how do you solve an equation of this kind? But in the beginning, we will first consider equations which are only homogeneous equations. So in other words, there is no external force. So let's just rub that out for the time being. We will bring in that force, external force, in some of the later lectures. But for now, there is no external force. So we are only going to study differential equations which with a zero right-hand side or zero input. And we will learn how to solve them. Okay. So what I mean by solve is to actually find out what x is. X will be a function of t, but what function it is, that you have to find. Okay. So let's just now try to solve this differential equation. Okay. Well, the one thing that you can do, and one thing that has been tried and tested and it works all the time for this homogeneous second order linear differential equation, is that we try a solution which is called the trial solution. Trial solution. Okay. We don't know what x is as a function of t, but we try that xt perhaps is an exponential function where we put some constant times t. Well, of course, we don't know what m is, but we want to try this as a solution for this. If we do find a correct m for which this does become a solution, then this is no more a trial solution, but an actual solution. And that's the objective. So let's just try that out. Let's just, instead of x, we put e to the power mt. So if you double differentiate e to the power mt with respect to t, you will get m squared because this m will come down 2 times and the exponential will remain as it is. Then you have the second term where there's a constant b. Now, again, instead of x, you have e to the power mt, which is differentiated once with respect to t. So the m comes down only once and the exponential part remains as it is. And here there is a constant c and x is e to the power mt. The right hand side is 0. Now e to the power mt is common in all of them, and since e to the power mt is never 0, you can take that out, you can cancel that out, and you are left with this quadratic equation in m, which is m squared plus bm plus c equals 0. So, and this equation has a name. It's called an auxiliary equation. Auxiliary equation, where from the trial solution, this constant comes here as the variable for the quadratic equation. And really, if you compare the x, the second order term is replaced by m squared, the first order term is replaced by m, and the zeroth order term is replaced by 1. Okay? So this is the auxiliary equation. Now, the objective was to find this m, the correct m for which this would become a solution. And now if I am putting that in here, I find this is the quadratic equation which will give me that m. So let's just solve this quadratic equation and you will have your correct m. But of course, there are going to be two roots of this because it's a second degree polynomial function. And so what are the roots? So from a basic formula for solving a quadratic equation, the two roots would be, well, the first root will be minus b over 2 plus the b squared minus 4c by 2. So I'm taking the positive square root term in the first root m1 and minus b over 2 minus root of b squared minus 4c divided by 2. Okay, so these are the two roots. Of course, now once we have the two roots, the question therefore is, what are the solutions then? So of course, e to the power m1, where m1 is given by these constants, if you calculate them, whatever the value is, then m1t is no more a trial solution. It is actually a solution because now you have the value for m1. And let's just call that x1, the first solution, one of the solutions. You also have a second solution for m2, which is e to the power m2t. Well, m2 is given by, if you calculate whatever it comes to. So the question is, what therefore is the solution? Well, they're both the solutions, so we'll just have to combine the two solutions in a manner which again would be the linear combination. So what we call the general solution for the differential equation, this given differential equation, homogeneous differential equation, will be xt some constant times the first solution plus another constant times the second solution. And if you write that out, this will be c1 e to the power m1t plus c2 e to the power m2t, where m1 and m2 are calculated by these formulas, and that's your general solution. This is a very particular kind of solution where c1 is 1 and c2 is 0. This is another one of those kind where c1 is 0 and c2 is 1. But of course, we combine both of them and we get the general solution. And it makes sense to have two constants in the general solution because we are solving a second order differential equation. So in order to recover what x was as a function of t, because x has been differentiated twice, to recover it as a matter of intuition, you can think of x being integrated 2 times. So you are bound to have two constants, which kind of feature here in the general solution, and you know, we are on the right track. Of course, depending on various things now, you can have various cases. For example, if now these m1 and m2 can be of various kinds. If b square could be greater than 4c, in that case, m1 and m2 are real numbers. B square could be less than 4c. In that case, m1 and m2 are imaginary numbers. So depending on which case you're dealing with, the general solution will then pan out accordingly, and we will actually get various cases. So I'll just write down the various 3 cases here and we will discuss them in the next videos. The first case that can arise from here is that if b square is, let's just do the less negative one first. B square is less than 4c. In that case, these will become imaginary numbers because you have a square root of a negative number. So M1 and M2 would become complex numbers, and that's the case of what is called underdamping. Damping refers to how much resistance there is. If it's underdamped, it's going to continue to oscillate for a while before it comes to a standstill. The second case could be that b square is greater than 4c. That's the case of overdamping. In other words, the b represented the resistance, eta by m. And if the resistance is very high, or the friction is very high, then that's the case of overdamping, where there will be very minimal oscillation. You pull it down, and the resistance is so much that it just sort of, maybe it crosses one time, and then it comes to a standstill. Okay? So that's the case of overdamping. There is another case, which is the case where b square is equal to 4c. So the case where this is 0. In that case, M1 and M2 are the same. So M1 and M2 are the same because because this is 0, they're both equal to minus b by 2. That's the case of what is called the critical damping. It also has a special name. It's called resonance, and it's a very interesting case which we will take up in one of the videos later. I left out some space here because there could be another case where b is 0 altogether. Okay, b is less than 4c, but what if b is 0? In that case, if b is 0, then of course you have minus 4c, so it's a square root of a negative number. So it will still be a complex number. M1 and M2 will still be complex because the b is 0, so you have a minus 4c underneath the root. But if b is 0, these terms, the real terms will also be 0. So you have a purely imaginary number. Okay, that's the case that's the case of undamped oscillation of simple harmonic motion, where it is not damped at all. If b is 0, it means that there is no resistance. And if there is no resistance, it is going to move up and down in a simple harmonic motion in an undamped fashion. It will never stop. And that's the case of undamped simple harmonic motion. We will take up each of these cases in the next few videos. But for now, this is what the general solution of a differential equation, second order linear ordinary differential equation looks like. Thank you.